Well, welcome back, men. I hope everyone had a great spring break. Do want to let you guys know that I definitely miss being in the classroom. I definitely miss interacting with you guys. This will be the last chapter that we will cover. I've got some good news and some bad news. Good news is that the AP exam will only cover the material from chapters 1 through chapter 10. So I just feel like if you were to take AAP or a statistics class in college, that you would need these chi-square procedures. So Mr. Spears and I, have decided that we're going to go on and teach you guys chapter 11. Good news about the AP exam, I guess, is that it is 2 questions. There will be free response questions, and you will have 45 minutes to take that exam. Your guess is as good as mine of how they could determine what is considered a passing for just 2 questions, but we'll go down that path when we need to go down there. But we're going to start with chapter 11 today. It's a short and sweet chapter, and we'll get through it, and then you guys will have a chapter 11 test. I will share my agenda with you, and then from there we'll go on into AP review. So congratulations on the school year, and congratulations on completing AP statistics. So chapter 11, we're going to learn the chi-square procedures. So sometimes we want to examine the distribution of a single categorical variable in a population, and we use the chi-square goodness of fit test. So the chi-square goodness of fit test. It allows us to determine whether a hypothesized distribution seems valid. We can decide whether the distribution of a categorical variable differs for 2 or more populations or treatments using a chi-square test for homogeneity. We will often organize our data in a 2-way table. It is also possible to use information in a 2-way table to study the relationship between 2 categorical variables. The chi-square test for independence. Allows us to determine if there is convincing evidence of an association between the population at large. So the chi-squared statistic. We're just going to take a look at an example here and kind of work our way through it. Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about their color distribution of its M&M's milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% of each browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blues. The one-way table summarizes data from the sample of M&M's milk chocolate candies. In general, one-way tables display the distribution of a categorical variable for the individuals in the sample. The sample proportion of blue M&M's, so p hat in this situation, we have 9 out of 60 of those M&Ms, and 9/60 is about 15%. Since the company claims that 24% of all M&M's milk chocolate candies are blue, we might believe that something fishy is going on. We could use a one-sample z-test for a proportion to test the hypothesis that the true proportion of blue M&Ms is 24%, or it is not 24%. We could then perform additional significance tests for each of the remaining colors. Performing a one-sample z-test for each proportion would be pretty inefficient and would lead to the problem of multiple comparisons. Problem. Performing a one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a distribution that differs as much from the one claimed by the company as this bag does. So, the solution is we need a new kind of significance test, and that's called a chi-squared goodness of fit test. And in the chi-squared goodness of fit test, the null hypothesis should state a claim about the distribution of a single categorical variable in the population of interest. So, the company's stated color distribution for M&M's milk chocolate candies is correct, and the alternative is that the company's stated color distribution for M&M's is not correct. The idea of a chi-squared goodness of fit test is this. We compare the observed counts from our sample with the counts that would be expected if the null is true. The more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. Assuming that the distribution stated by Mars is true, 24% of all M&M's milk chocolate candies are blue. For random samples of 60 candies, the average number of blue M&Ms should be 0.24 times 60 is 14.4. This is our expected count of blue M&Ms. Using this same method, we can find the expected counts for the other color categories. I'll let you take a moment and check the math there. To see if the data give convincing evidence against the null hypothesis, we compare the observed counts from our sample with expected counts, assuming the null is true. If the observed counts are far from the expected counts, that's evidence we are seeking. So looking at our side-by-side bar graphs here, we see some fairly large differences between the observed and expected counts in several color categories. How likely is it that the differences this large or larger would occur just by chance in the random samples of size 60 from the population distribution claimed by Mars? To answer this question, we calculate a statistic that measures how far apart the observed and expected counts are. The statistic we use to make the comparison is the chi-squared statistic. The chi-squared is a measure of how far the observed counts are from the expected counts. The formula for the statistic is chi-squared equals the sum of observed minus expected squared divided by expected, where the sum is over all possible values of that categorical variable. So here we have our chi-squared, so it's 9 minus the 1440 squared divided by 14.4. 8 minus 12 squared divided by 12. Add that to 12 minus 9.60 squared. The difference, 12 minus 9.60 squared divided by 9.6. We do that for each one, and we get a chi-squared value that is 10.18. So think of chi-squared as a measure of the distance of the observed counts from the expected counts. Large values of chi-squared are stronger evidence against the null, because they say the observed counts are far from what we would expect if it was true. Small values of chi-squared suggest that the data are consistent with the null hypothesis. The sampling distribution of the chi-squared statistic is not a normal distribution. It is a right-skewed distribution. So the chi-squared is a right-skewed distribution, and the values are always positive. Chi-squared can never be negative. Think about it. We're taking a difference and we square it, so we get a positive value. When the expected counts are all at least 5, the sampling distribution of the chi-squared statistic is close to a chi-squared distribution with degrees of freedom equal to the number of categories minus 1. So in our situation that we had, we're just going to have all of our colors. We're going to take a look, and I forget how many colors that we have in our bag of M&Ms. 6, I believe, so it's going to have 5 degrees of freedom. We also saw that all of our expected counts were greater than 5. from the previous page. So, we computed the chi-squared statistic for a sample of 60 M&Ms to be 10.180 because all of the expected counts are at least 5. We'll follow a chi-squared distribution with 5 degrees of freedom. So we come over here and we see, well, where is that? We have 5 degrees of freedom. We had a chi-squared value that was between 5 and 10%. So our p-value is between 5 and 10%. It is greater than an alpha of 5, therefore we will fail to reject the null, and we do not have sufficient evidence to conclude that the company's claim color distribution is incorrect. Let's take a look at the conditions for performing a chi-squared test for goodness of fit. We need to know that the data come from a random sample or from a random experiment. When sampling without replacement, we need to check the 10% condition. And our large counts here is that all expected counts are greater than 5. Before we start using the chi-squared goodness of fit test, we have 2 important cautions to offer. The chi-squared test statistic compares observed and expected counts. Don't try to perform calculations with the observed and expected proportions in each category. No, they need to be a number, so observed counts and expected counts. When checking the large sample size condition, be sure to examine the expected counts, not the observed counts. So, suppose the conditions are met. To determine whether a categorical variable has a specified distribution in the population of interest, expressed as the proportion of individuals falling into each possible category, our null hypothesis is that the stated distribution is correct, and the stated distribution of categorical variable in the population of interest is not correct, will be my alternative hypothesis. I'm going to start by finding an expected count for each category, assuming that the null is true, and then I'll calculate my chi-squared statistic with n minus 1 degrees of freedom. So we're going to run our first test. This is a problem that was in Malcolm Gladwell's book Outliers. Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is a cutoff date for youth leagues in Canada. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 National Hockey League players from a recent season was selected and their birthdays were recorded. The one-way table below shows the birthdays of these 80 players. Do these data provide convincing evidence that the birthdays of all NHL players are evenly distributed among the 4 quarters of the year? So, we're just going to carry out a significance test. And because we don't have a parameter of interest, we're going to follow Hantum's. So I'm going to start off by claiming what is the null hypothesis. And the null hypothesis is the birthdays of all NHL players are evenly distributed among all 4 quarters. So the birthdays of all NHL players are evenly distributed among all 4 quarters. And the alternative is the birthdays of all NHL players are not. So the birthdays of all NHL players are not. evenly distributed. So we've got our H. I'm going to test at 5% significance. Alright, so there's the H. I'm going to check out the A. It says a simple random sample of 80 NHL players were taken. Alright, I need to calculate the expected. So we had 80 and we had 4 quarters. So 80 divided by 4 is 20. So my expected, I need to make this column. We're going to have 20, 20, 20, and 20. So all expected counts at least 5. And lastly, it is safe to assume there are more than 800 NHL players. I think for one season, that is safe to assume. All right, so I got the assumptions taken care of. I'm going to run a chi-squared goodness of fit test. I want to calculate my chi-squared statistic. So that chi-squared is equal to, so that was 32 minus 20 observed minus expected, quantity squared divided by expected, and plus 20 minus 20 squared over 20, plus 16 minus 20 squared over 20, plus 12 minus 20 squared over 20. When I do that, we get 11.2, and the degrees of freedom is equal to 4 minus 1, which is 3. So I need to calculate my observed value. So the probability that chi-squared is greater than 11.2 is equal to, and we could do a chi-squared CDF. Chi-squared CDF, where lower is 11.2, upper is 1 times 10 to the 99th, and we have 3 degrees of freedom. When we do that, you get 0.0107. Since P is less than alpha, 0.0107 is less than 0.05. We will reject a null. And since I'm going to say that we have convincing evidence that the birth months of NHL players affects whether or not they play in the NHL. So yes, we will reject it all. There is convincing evidence birth month effects. And you guys could go on and write that out. I'm going to stop here today, and you guys will finish 2 more examples tomorrow. but I would just like for you guys to check the agenda. I'll post that on Schoology as well as on Plus Portals. Schoology has been down, so just bear with me and just check the assignment off of Plus Portals. Take care, men. Have a great day.